Hello everyone, I am SOMANI, BTech first year student at IIT Roorkee, DACI branch. Today I am going to present my C++ project on determination of determinant of an n cross n square matrix in C++. So let's get started. So we are going to use the cofactor or Laplace expansion for the determination of the determinant of the n cross n matrix. So let's say matrix A is defined as like this, n cross n matrix. So now the det A, what det A represents? Det A represents the determinant of A, just that's simple, and it's equal to the summation. See, we are expanding the determinant across along the first row. Along the ith row in this formula. When we expand the determinant along the ith row, the determinant of A is given by the jth element of the ith row multiplied by the determinant of the minor matrix of that element multiplied by the minus 1 to the power I plus j. The minus 1 to the power I plus j is for carrying the alternating signs in the expansion, and that's it. So let's move ahead. Now see, the expansion can be done along any row or any column, but we are going to use the expansion specifically along the first row, as say for any row or column the determinant is going to be same after all. So the most natural choice or the most easiest choice which appears to you or to me or whoever is that we use the expansion along the first row. Now see, the expansion along the last row is also going to be equally simple and all, but that's okay. Now see what we have done in the determinant formula. Since we are expanding along the ith row, I have just first row I is equal, we have just put an I is equal to 1 in this formula. So let's that's it. Just I plus j becomes 1 plus j, aij becomes a1j, and m1j, it becomes m1j. Now what is m1j or mij? Mij is the minor matrix of the element aij. What is the minor matrix? Minor matrix is the matrix formed after removing the ith row and the jth column, or we can say the matrix formed by removing the row and column of the particular element. Like for an example, for this 3 cross 3 matrix example, if we take for the first element here, we are expanding across the first row. Okay. So in this example you can see for the first element, that is the a11, the minor matrix comes when we delete the first row and the first column, that is this matrix a22, a23, a32, a33, that's all. So that's simple. Minor matrix is formed by deleting the ith row, jth column, and we are going to do the expansion along the first row because it's simple. Okay. So now we have understood what determinant is, so let's move ahead with the code work. Now see, what do we want from the user is we want the user to give us input in the form of a matrix, and the output the user is wanting is the determinant of the matrix. So we need some working function on this input to give this output in the form of determinant. And now see, what is determinant of A is given by multiplying the element to its minor matrix and doing the summation and all. But the minor matrix, what now see, this minor matrix has an order 1 lesser than the main matrix. Okay, so if this so what we are actually doing, we are reducing the order of the matrix with that cofactor expansion. So what we need to do, we need some recursive function which continuously reduces the order till it reaches some convenient order like 2 or 1, so that we can directly claim by explicitly writing the determinant of that particular 2 by 2 matrix and such. So let's move ahead now. Okay, see, whenever you write a code, it's good to pre-think in your mind of what steps will you follow in writing the code. It's always good for someone like for a beginner like someone like me to break down the code into steps. So when you write the code, you don't get into confusions, and it becomes a straight path that you need to move along that path to solve that problem. Okay. So now what we need to do? We need to firstly we want the user to give the matrix size as an input, because we are finding for a general case n cross n. So we need the user to give the input of the size when the user gives the input. Then the second thing is that since the matrix size is not known to us when we are writing the code, we need to dynamically allocate memory for the matrix. Okay, so we do the dynamic memory allocation for the matrix. Then now we have done what? We have decided the size of the matrix. We have some dynamically allocated memory for the matrix. Now we take input from the user, input of the matrix from the user, and now what we have? We have input of the matrix and the size of the matrix defined. Now we need to feed the size and the matrix into some function, some determinant function, which calculates the final determinant and returns it. Yes. So now, as we have seen, that the cofactor expansion is working on some recursive method that you break down the main matrix into a one less order matrix, and so on and so on and so on until it converts into a convenient 2 by 2 matrix, so that we can easily explicitly write the determinant. Okay. So we feed the matrix size for determinant calculation. The function puts recursion over the order to reduce it. And now what? See, when we go back, now here, this term det mij or m1j is needed for calculation of a. So first, m is needed itself. So we need the minor matrix for the next steps. So now obviously for n less than 3, like n is equal to 2 or n is equal to 1, we can explicitly write the determinant and give the final output. But for the higher cases, obviously it becomes complex, and what we need to find is we need to define some minor matrices for each element. Okay. So the minor matrix will be the function. We need the parameters, the element and such things in the main matrix. Then the minor matrix is defined again, and it get again fed to the determinant function, which again, if it's not n is equal to 1 and n is equal to 2, again it goes through the same process until it reduces the big matrix into small, and it becomes a 2 by 2 matrices, the summation of some many 2 by 2 matrices multiplied by something and something, and then it gives the final output. So now we have understood the workflow. Let's move ahead. This is the workflow in the form of code also. Like we take the input from the user, give it, and then we dynamically allocate the memory for the matrix, take input of the matrix from the user, then we call a function determinant and feed it the matrix and n. It goes to the determinant function. If n is equal to 1, 2, it's simple. N is equal to 3 case, it will again form the determinant of the minor matrix. It will call the minor matrix. Minor matrix will be defined, and again the minor matrix will get returned into this determinant function at this loop until it breaks down into n1 of n is equal to 2 case. Okay, so let's move ahead with the code and understand the code on the broader basis. Okay, so what we need to do is to take the matrix size input from the user. Now we simply initialize an integer, some say n, and the user give it as an input, and now that's simple. What we regularly do, like take an initialize integer, take input from the user. The cout thing and l is just good practice for better representation, say. Okay, and nothing else. Now again, good practice is to ensure that the user doesn't feed some non-natural number, because the size of the matrix should be a natural number. So we should ensure that the code doesn't continues on returning some non-natural number. Okay, so we can simply ensure it that if n is less than 1, it should count some error message that like size of matrix need to be a natural number like this, and it returns 0. It might return 0 means it ends the main function, and it ends the code. The code doesn't go further. Now see, the if else is not required here. You can just simply just use the if, return 0, and simply further write the code. This method is not required. This not much of a thing to bother about. Now the next step is dynamic memory allocation of the matrix. Now since the matrix size is initially unknown, you need to dynamically allocate the two-dimensional array or the matrix. So now it will be done in 2 steps. Firstly, what you will do, you will allocate an array of pointers, and then to every that pointer you will allocate another array. To each pointer you will allocate an array corresponding to that. Okay, so that will become something like an array of arrays that's equivalent to matrix. Okay, so what this double asterisk matrix is equal to new double star and all this, what this do? Now when we simply dynamically allocate one dimensional array, you simply use double star matrix or the data type star matrix asterisk matrix. But here you use the data type as double star, so this matrix is an array of data type double star. So double star, so it's a pointer again. Now in the next step, you after allocating array of pointers, you allocate each separate array each row. Okay, so means like, okay, this is like you put a loop. Now what this matrix I represents, matrix I represents the I plus 1th array of the pointer. That's simple as that. And again you dynamically allocate that. Okay. Let's move ahead. Now that's some terms. Now for understanding it in layman language, like what is matrix I? Matrix I is the I plus 1th array of size n, and matrix ij is the j plus 1th element of that I plus 1th array. Okay, this becomes simple. That it is an I plus 1th array, and this is j plus 1th element of that array. That's it. Let's move ahead. So now what is the next step? You have taken the input of the size from the user, and then you have dynamically allocated the memory for the matrix. Now the next step needs to be taking the input from the user of the matrix elements. Now we simply put a nested loop where the variables ij goes to from 0 to n minus 1, and obviously again writing this row here is just a good practice that you make a good user interface, as we are already doing with some things like here also, like cout and l is just again for a better user interface. You leave lines, and that's all, not much of a business for now. Now the next step is the main step that you you have what you have done. You have decided the size of the matrix, and you have taken the input of the matrix from the user. So now you need to display the determinant of the matrix, and you call some function determinant and feed it the matrix and its size, which goes to the function. Now we have taken obviously the function type is double, because since the entries are taken as double data type, and feed it the size and the matrix. Now for n is equal to 1 and n is equal to 2 cases, the determinant is simply calculated, explicitly can be calculated and can be returned, and that's over. But the complexity comes when n is greater than equal to 3. Yes. So now what we do, we put a for loop. Now you see here this summation is replaced by this for loop. So what is happening? This is a summation, something. Okay, so we initialize this sum as 0, and with each counter increasing on that summation, like from j1 to n, whatever that counter was, this summation is get redefined, and its value get updated on this loop. Now that's it. And the if else statement, why I have put in the if else statement, it's just for checking the even or oddness of the sum I plus j, and nothing much. Like it displays plus simply adds it if, since I is 0, if j is even, it simply adds the next term, and if else it will just subtract the next term. Not much of a deal. So let's move ahead. Okay, now understanding the recursive function, the determinant's recursive function. Now what is a recursive function? A recursive function is a function which calls itself. So now what we are doing, for n greater than equal to 3, the determinant calls itself again and feeds the function, its own function, the lesser sized matrix called minor matrix. We will need to define that minor matrix, but now let's firstly understand what's written here, that the summation, as I've written here, that the summation is carried by the loop, for loop, it is carried by the loop, and the variable sum is continuously getting redefined. If else is just for carrying the alternating sign of the terms. And see what happens when we calculate the determinant. We need to call the determinant function again itself for n greater than equal to 3 cases, as I've written here, that we break it down to smaller matrices, as I said earlier, to or we can say the smaller matrices or the minor matrices continuously. So we need to use this recursion thing here. That's simple. Now the last part, we define the minor matrix. Now since in the last slide, see, we have redefined the sum as the earlier sum till the last counter plus minus 1 to the power I plus j is carrying by this loop times the determinant of the minor matrix of this element. Since we are expanding across the first row, the jth element of the first row multiplied by the determinant of the minor matrix of that element. So now the only thing left is to feed this determinant a minor matrix. So now we need to feed this determinant a minor matrix. If after feeding it, what it will calculate, it will again the loop will get finished, and that's all. So the last step is to find the minor matrix. Now let's move ahead. Now the minor matrix, see what happens again when you need to define minor matrix data type as double star again. This can be done as a mistake, that you define the minor matrix data type as double. Again, since it's returning matrix data matrix, the data type should be double star again, because it's also dynamically allocated. Okay. Now we are feeding this minor matrix function the initial size of the main matrix. The main matrix we are feeding it, and the element, since we have fixed the first row, we only need to care about the column number, and the column number is carried by this. So we are feeding it some parameters, and for those parameters it will find the minor matrix. Now again, since again the size of the minor matrix is not defined, again we need to dynamically allocate n minus 1 cross n minus 1 matrix for that new matrix. Say as we are seeing here, matrix prime. Okay, in the similar fashion we have done in the last thing, and that's simple. But for the next step, now the last thing what is left is to allocate the minor matrix elements its values corresponding to the main matrix values. Now the last, okay, see, what it will have size minus 1 elements. Now n minus 1 or size minus 1, because since n is it will continually keep change, we say new variable size. It will have size minus 1 cross size minus 1 elements in its matrix. Now like say, now there are two cases, that you till j, and after j, the jth element you have, the jth column you have chosen, till that what you need to do is you don't need to care about the column number. The column number of the new matrix prime element and the main matrix, feed it to the function. The column number will be kept same, but for k is equal to j till higher, till the final entry, the column number will also increase by 1, since means the column number of the matrix prime will be 1 lesser than the main matrix, since we are skipping one column. And for the whole thing, the row number will be done, the row thing will be done for the whole thing, because we are not using the first row, so every ith row of the main matrix will corresponding to the I minus 1th row of this matrix prime. So now we have allocated the elements for the matrix prime, we have defined the matrix prime, we will return the matrix prime to that determinant function. So now how the loop is working, finally we are calling the determinant function and feeding it n in matrix, and for n is equal to 1 or is equal to 2, this case is simple, but for higher cases the determinant will again call itself by using some minor matrix. The minor matrix will return to the determinant function again, and then again the function will check that the minor matrix order is 1 or 2, then it's a simple case and leaves with the final value. But again for greater than equal to 3 case, lesser size matrix again goes for the loop, and again it continues until it converts into some sum of 2 by 2 matrices, and it will leave with the final value. Okay, so now we have done with the function, we have done the whole thing with the function. Now what we finally need to do, we need to display the determinant of the matrix. We simply count the determinant of this entered square matrix is this, determinant function's value will be displayed here. Now again one thing is very good, that at the last what you need to do is you need to free the memory of dynamically allocated matrix. To avoid memory leaks, it's a good practice to always free the dynamically allocated memory. Now what the first line do, the first loop frees each row, that like how we have allocated in the reverse sequence, we will delete the data, like we have allocated the rows later, so now we will free the rows first and then we will free the array of row pointers. Okay, now let's see some sample cases. For like we have done with the code, let's see the final code and some final solved cases solved by our code in the display. So here's main code. Obviously we should always start reading the code from the main function, because that's where the working process starts. Okay. Firstly what we do is taking the input of the size of the matrix from the user, leaving a line ensuring whether the input is a natural number or not. Then we dynamically allocate the two-dimensional array for the matrix. The same, firstly we allocate an array of pointers and then allocate array to each pointer. And that's as simple as that. And then we take input of the matrix from the user. I have written row here, I+1 for just better user interface, and just put a nested loop over I and j and enter on the n cross n entries. Leave a line for better representation again, and then want to display the determinant, you need to feed the size of the matrix and the matrix itself to the determinant function. Okay, and again we call the determinant function, it goes here for n1 and n2 cases, it simply explicitly writes it. For n greater than 3 case, now it becomes complex. The double sum 0, the sum, the redefining of sum, and the for loop cares about the summation, the sigma sign as we see, and the if and else statement cares about the alternating signs of the terms in the expansion. Obviously, and the main thing happens here, that the sum is continuously redefined by either plus getting added or subtracted by J plus 1th element of the first row multiplied by its minor matrix determinant. We call the minor matrix determinant and it goes to minor matrix function, it gets feeded. We need the size of the main matrix itself, and the jth element, j plus 1th element, for which the minor matrix need to be defined. Again, a dynamical allocation of memory like the main matrix. Then again, the values assigning of the minor matrix, but here obviously the size becomes size minus 1 in size minus 1. So we just need to ensure that we delete ith row, which is the first row, and the jth column. Ith row deletion is handled by I and I plus 1, writing I plus 1 here, and the when we are writing for jth element, j plus 1th element, it is cared by these two. We break it down into two, and that's it. It returns the minor matrix into this. Again, it calculates the sum, or if again, like for calculating the determinant of the minor matrix, it feeds the, now the determinant is called, again it checks whether the minor matrix size is 1 or 2 or not, and again it recursion alternate breakdowns into some summation of something, multiplication with some number multiplied with the 2 by 2 matrices determinants. Now the final sum is the determinant we need, and this get feeded into the final output display, and we leave a line. That's this is just not even required. Okay. Obviously, the freeing of dynamically allocated memory is just for good practice, that you free the dynamically allocated memory so that there are no memory leaks. You just prevent that. Okay. And you just firstly free rows and then free the array of row pointers in the reverse order, or how you assign the values. That's a good way to learn this. Okay, so let's check for sample cases now. Say for n is equal to 2. Now simple case. For a simple matrix n is equal to 2, it will directly explicitly it should explicitly give us the output of, let's say, 2, 3, 12, 12. It should give output minus 12, as we can simply calculate it, and that's just the answer coming. Now that is a simple matrix. Now for a bigger matrix, say a 6 by 6 matrix, where obviously we don't calculate such type of determinants in real daily like work by ourselves. So again, here the program actually where we need the programs. Okay, so say a 6 by 6 matrix. Just take an simple example. So 6 by 6 matrix. You put consecutive, or maybe like simply just copy all the rows. What will happen is that obviously we know the property, but the function will just calculate in the thorough way. Obviously, we know the property that if two rows are same, then the determinant becomes 0, but the function will simply calculate it and the determinant comes as 0, so that's a good thing. Now one more thing that what if the if statement we have added that if we enter some non-natural number value, then it should display say if it's not a non-natural number value, it should display an error message. If it's a non-natural number value, it displays an error message that the size of matrix need to be a natural number. So that's it. We've seen for a bigger matrix, it's how it's calculating. For a 2 by 2 matrix, it's just explicitly writing. For a bigger matrix, it's just putting the recursion over the order of the matrix. And for non-natural numbers, it's giving us an error message. Yes. So that's it for the video. Thank you guys. I hope you like the video.